About some of the things I've been working on to try and make Smokeview a better partner to FDS for visualizing data. So I'm going to talk about improvements to the visualization of smoke, how we're using the video card to do some of the computations, and making better use of color to visualize some of the FDS data. As you all know, the tools that we use to do our simulations have just improved tremendously over the years. When I was first involved in scientific computing at Mobil Oil, we had a Cray 1, and it was able to perform at the stupendous rate of 12 megaflops. That's a million floating point operations per second, and we thought that was a very fast computer. And at the time, we could solve cases as large as 10,000 grid cells, and we thought that was fantastic. I did some Google searches recently and discovered that the smartphones that we have can outperform a Cray 1. So an Android smartphone at 36 megaflops and similar results for an iPhone. And I performed a LinPack benchmark on the Linux cluster that we have at NIST, and I got about 80 or 90 gigaflops per node, and multiplying that by 32, that's about 2 teraflops. So the question is, and at first, you know, there's the problem, and wouldn't we all like to have these kind of problems, is what do we do with all the data that gets generated? And that's sort of my job, is to take all this data and make sense of it with the visualization program Smokeview, because your eyes, with the bandwidth of being able to look at pictures, can get insight into the data much better than just looking at tables of numbers. Now, so basically I'm going to be talking about lighting calculations. Well, OpenGL, which is the software tool that I use to present the data, does a lighting calculation in the background, so that when you're looking at the blockages, I have to tell it the direction that the blockages are pointing, and I create a virtual light source within Smokeview that's there solely to make the geometry, give it more of a three-dimensional sense. So you can see in the in the image on the left is unlit. I've turned off the lighting so that everything looks flat. In the middle, you see some faces of the blockages are darker than others, and so that helps you see a three-dimensional sense of the scene. The methods that we're using to visualize smoke have evolved. So starting out, we're using, one of the first methods was just to use tracer particles. So the particles move through the flow, and you can kind of get a sense of the movement of the air or smoke in your simulation. Then we have a traditional scientific view of the data, which is just an animated sequence of colored images where the colors represent the quantities that we're trying to simulate. Then we have animated isosurfaces where the location of the surface represents some particular value you're interested in. It could be a critical temperature, it could be some heat release rate that's important to you. And then the next method is a more realistic way of looking at the data, which is representing the smoke in terms of transparencies. Sort of the different types of interactions that you can have between light and smoke are illustrated in this top row. So when the arrow, your virtual kind of packet of light hitting a a little ball of smoke. You know, it can be absorbed or it can scatter. And so these first two items will cause the light to degrade, to diminish. If the smoke is hot enough, or if you're in a combustion region, the light can increase. And then you can have light scattering from other directions into the line of sight and also cause it to increase. Now, if you write out all these terms in a mathematical way, you have what's called the radiation transport equation, or the people in the graphics literature call it the volume rendering equation. What's interesting is I took this equation from a graphical textbook, and then I went to Kevin's and Jason's and others and Randy's technical guide, and I just wanted to make sure that things look the same, and lo and behold, the equations are the same. Now, what I'm doing is I'm going to be solving these equations for a different wavelength. Instead of solving it for heat, I'll be solving it for light. Now, right now, I'm only solving the equations for the first two terms. I'm not handling the in-scattering or directly the emission. One other point is that this full-fledged partial differential equation for the light intensity, if you do neglect these last two terms, you can solve those equations and you get Beer's law, which is what I'm using to account for the opacity of the smoke. Now, this is just an illustration, a schematic of how I'm solving the smoke now. Now, you never see Smokeview in this view because, well, first, the way I'm drawing the smoke is I'm drawing a series of parallel planes, each plane corresponding to a grid plane that you're solving in your FDS simulation. Now, when you're looking at it in Smokeview, I'm always drawing it so that you're looking at it full face on. So I want to orient the plane so that they're as perpendicular to you as I can make it. Now, for the purposes of this illustration, I turn that off so that you can see them from the side. Now, each of these planes has a color and a transparency. The transparencies are pre-computed in FDS using Beer's law. So basically, we're taking the soot density that you're computing the flow of, the transport of soot, and in FDS, in a pre-processing step, we're saying, well, let's take the soot density, the step length between the grid planes, and the mass extinction coefficient, which is just a proportionality constant, to map the density to an opaqueness or a transparency. So basically, this is a schematic of that. Now, as one thing that we had to do in Smokeview is if the pre-processing step was done edge-on using the parallel distance between the two planes. Now, you're not just looking down the line, you're also looking off to the side. So the path lengths are longer as you go off to the side. So one of the things that Smokeview would do in real time would be to correct the opacity based upon the longer path length. And also, there's an option to skip frames, so we would use the same idea to increase the opacity of the smoke planes if I'm skipping them. Now, there's a problem that occurs for large cases, and sort of the general thing I've been trying to do with Smokeview is to make Smokeview better able to handle the large cases that all these fantastic computers that we're getting, will be able to handle. The problem occurs is that as you have smaller and smaller cases, the grid planes are going to get closer and closer together, so the delta X is going to get smaller. So you're going to have more and more of these transparent, partially transparent planes, so the contribution of any one of these planes is going to be less and less. Now, if you had perfect and full precision arithmetic, it wouldn't matter. You know, you would just combine all these things together and it would just all come out to the same thing. But the problem occurs is that in most video cards, you've only got 8 bits to represent the opacity or transparency of whatever you're trying to draw. So once the transparency of your smoke plane gets below 1/256th, it's going to be identically 0. And in fact, you know, I've seen, you know, Randy had some cases where, you know, he said, "Glenn, where's the smoke?" And that was what was going on. So what this has led me to do is to change the approach of how we're modeling this smoke visualization in Smokeview. And that is, instead of integrating from one plane to the next and just storing these intermediate quantities, I want to integrate across the entire mesh in one fell swoop using a line integral. So that way, all the intermediate quantities are available to me in the CPU, so there's no loss of precision. And, okay. Now, a little bit of an aside, I want to talk briefly about color. The 2 steps here are I'm using, presently using soot to come up with an opacity of the smoke and using temperature to come up with the color of the smoke. Now, I want to talk a little bit about color and its use in representing data. And why it's important for coloring smoke or anything else we color. In the new version of Smokeview, there's a capability of creating your own color bar. You don't have to use the one that's the default. Now, basically, for those of you familiar with tours, it's very similar in idea to creating a tour that goes through the scene, in that you've got 3 coordinates, red, green, and blue, which I'm representing as 3 coordinate axes. And so then you can just pick nodes along a path that would select your color bar. And so the 3-dimensional view on the left is just the 3-dimensional representation of the red, green, blue color bar that you see on the right. Now, this is an example I give a lot to talk about the importance of color and why choosing the wrong color bar can mislead you or hide the meaning of the data that you're trying to present. Now, if you haven't seen this before, you know, you could just say, well, this is just a data set representing a bunch of numbers going from -35 to +1000, whatever units they are. So you look at it and you say, well, there's some blues and there's some greens and yellows and a little bit of reds there. And so oftentimes I'll ask, what do you think that is? Now, right now, I will tell you that 0 is a very important value in this data set, but this color bar is hiding that fact. Now, if I present this plot using a discontinuous color bar, using shades of blue for values less than 0 and shades of greens and browns for colors greater than 0, then you get this, which is obviously a map of the southeastern United States. So this picture was kind of why I wanted to give you all the chance to use your own color bars, because oftentimes, you know, maybe 100 degrees C is an important value or some other value, and it's often, if you can choose a discontinuous color bar, it's often better to use that. Now, I want to talk a little bit about what I'm doing to perform this line integral. So basically what I'm doing is from the observer's point of view, I'm shooting a ray through the scene, through every pixel on the screen. Now, for each pixel, I'm doing a line integral. Now, the first step is to get the data, in this case, soot densities and temperature, into the video card. And so then, as I'm computing this line integral, I need to retrieve in each one of these boxes that represents the discretization of the integral that I'm solving. I need to retrieve a density and a temperature. Now, I use the density to integrate over this little box to get the transparency, and I use a color map, which is basically whatever color bar I'm using to get a color. Now, if I want the picture to be realistic, I want it to look like a real smoke plume, then the color map that I need to use needs to be based upon real physics. You know, maybe a black body temperature curve. Now, the equations in the blue box I'm not going to talk about, but these are the equations that the GPU is using to combine or collapse all the colors in each one of these boxes. So you see 6 boxes in each of these 2 line integrals, and each box has a color and a transparency. So what we're doing is I'm collapsing that box onto the screen and drawing one slice instead of, you know, in this case, 6. Now, this just shows an example. Now, what you see is I'm letting you see the smoke from the side. So I'm drawing the smoke on the surface. Now, this is the way you'd see it in the real Smokeview. So then I'll turn that off. I've frozen it. And so that's what's actually being drawn on the screen. Well, this is just an example of one of the cases that Randy was showing in his talk. Now, the encouraging thing to me is I sort of had a fallback position. I was expecting this to be pretty slow because I wasn't sure how much work it would take to do all these computations, because I am doing it for, you know, literally every pixel on the screen using what are called vertex and fragment shaders. Amazingly, this visualization is occurring at the same rate at which I'm showing it in this movie on the screen. That's 30 frames a second. Now, what that means is that that's 30 frames a second with compromised physics. Well, if we want to add more physics, the scattering and so forth, we have room to do that and still have something manageable. So the challenges of this new method for drawing smoke is it takes a lot of memory. For this computation, it's the mesh is 96 by 64. There's 16 meshes with 300 frames. That's 21 gigabytes of data. Now, the way I was doing things before in Smokeview is I would load the entire data set at one time before I did anything. Well, that would take a long time. For this, I just estimated, on a very nice system that would take 3 minutes to load. So some of the things I'm doing to get around these problems is I'm compressing the data to make the data set smaller. I'm using the GPU to make the computations quicker. For this method of drawing smoke, I'm loading the data in the background. So you can load the data and you can start seeing it at the same time. Now, obviously, you can't see it past the point at which you loaded it, but it just kind of cycles each time up to the point you've loaded it. So it just makes it a little bit more convenient. Now, for very, very large cases, what we've discovered recently is Susan Killian in Germany discovered a feature of Linux that lets you basically create a virtual Windows terminal on the computer. Now, what that means is that you can run Smokeview. You can be in Maryland, and you can have your Linux cluster in Florida, and you can run this you can run Smokeview on this virtual terminal in Florida and create all your images and not have to move the data back to Maryland. And what load data as required means that there's a new feature in Smokeview that if you want to render a frame, you only need to render the data for that one frame. You don't have to render the whole thing. So you don't have to have a computer with large enough memory to visualize the whole case. You only need a computer with large enough memory to visualize that one frame. These are just some of the details of how you use it. Basically, I'm not using any new data formats from FDS. I'm using the 3D slice file to get my data I need to do the visualization. This just kind of shows some examples of how I might extend this method to consider the more interactions with light and the smoke. And this just shows for clouds how scattering can make a difference in how things look. So, kind of to summarize, the main idea of this new method is it's much more flexible. I have all the data I need to do whatever computations I want to do. So I kind of want to make Smokeview to be more like FDS in the sense that in the beginning you used FDS to do your computations and you used Smokeview to visualize the data. Well, it makes certain logical sense to do some of the computations in Smokeview. So there's no reason why Smokeview can't take on more of that burden. So anyway, that's pretty much what I had to say today, and so I'll thank you for your attention. I'll try and answer any questions you have.